Dear students, good evening. Last class we discussed about you know NMR spectrometer, right? NMR spectrometer. So, so what is said there in NMR spectrometer? So we say about the nuclear structure in the mixture. Nuclear structure in the mixture. So similarly, uh, we have one more method for analyzing the structures of the chemical compound, right? Structures of the chemical compound. So how it is possible? It is possible with other techniques like ESR, electron spin resonance, electron spin resonance. So with this, there is a small difference between NMR and ESR. ESR. Okay. Uh, it is ESR. You see the structure first of all. You see the structure of ESR. So electron spin resonance spectrometer, right? So uh, the basic difference between ESR and NMR is in the NMR spectrometer we are using electromagnetic radiation in the range of radio frequency, radio frequency, radio frequency range. So in the complete electromagnetic spectrum, we are using radio frequency radiation for analyzing the sample of the animal, right? But in this ESP, uh, electron spin resonance is also called electron paramagnetic resonance, EPR, electron paramagnetic resonance. In this, in the same electromagnetic spectrum, we are using microwave, microwave frequency for analyzing the sample, analyzing the sample. Remaining the same. Whole operation, what is said in the NMR, is nothing but this here. But only thing is, here we are going to use a frequency range is microwave frequency. So, see that electron spin resonance involves detecting a physical phenomena. What the phenomena? Absorption of electromagnetic radiation in microwave region by paramagnetic spaces, means paramagnetic electrons that are subject to an external magnetic field. So the sample to be analyzed that should be in the paramagnetic field, and then you apply some fixed, I mean, uh, micro frequency. Then when the uh, sample observes that macro frequency, it is reflected again. It is reflected again. That frequency is absorbed by the detected by the some special detector, micro detector, that's called diodes. So that will convert that diode will give some current. The change in current is proportional to how much is absorbed in the radiation is absorbed in the sample. So based upon this one, we can easily measure that, unlike this sample spectrum, right? See the diagram of this diagram. So there will be some different bands available in this S band, X band, K band, Q band. So each band having some wavelength and frequency. So S band refers to 3 gigahertz, X band of 9.5 gigahertz, K band 23 gigahertz, right? So the corresponding wavelengths and corresponding magnetic field we have to choose it. We have to choose for the analysis of the sample with this ESR. See the diagram, basic ESR spectrometer. Basic ESR spectrometer. This is the diagram. In this diagram, what are the instrumentation? It is a crystron, attenuator. This is called circulator, and it is a magnet, and it is a cavity. This cavity, within this there is a unknown sample, sample, and it is low. The cavity to this circulator, we are giving some diodic detector and some ammeter, which measures some unknown currents. So see that in this crystal tube, generally the microwaves are generated by the crystal tube. So suppose you want a microwave signal, how can you get microwave signal? It is generated with the crystal tube, and power levels adjusted with the attenuator. This attenuator, why we have to place here? We not adjust the power level. You want to get some desired power level. And there is circulator. The circulator routes the microwaves entering from crystal towards the cavity where the sample is mounted. So on this cavity, we are mounting the sample. So the circulator routes microwaves entering from crystal. So from the crystal, we can have microwave signal. The circulator gives some directions entering the microwave signal to the cavity. That's the meaning of it. So cavity means inside it is sample to the sample. So generally, majority of uh, EPR spectrometers meters operate at a frequency of 9.5 gigahertz. So 9.5 means what? See, X band. X band. So X band, this is the wavelength, and this is the magnetic field that is available. Okay. Then the radiation may be incident on the sample continuously or pulse. So continuously that radiation should be incidented, microwave radiation, or with discrete pulses with the help of pulse. The sample is placed in a resonant cavity which admits microwaves through an iris. So there is a looks like a slit. Through that, some microwaves are admitted to the sample, and the cavity is located in the middle of the electromagnet and helps to amplify the weak signals from the sample. So we are placing the cavity uh, within the magnet, within the magnet. So because of this external magnet, so it will amplify the samples, it will amplify the weak signals, weak signals from the sample. Then what happens, most of the external components, such as source and detectors, are contained within the microwave beach, and uh, the attenuator and field modulator amplifiers are also used to enhance the performance of the instrument. So, if you want the exact conversions, we need some external electronics by selecting attenuator, field modulator, amplifier, like this. And see this the instrument, and in addition to this, there is a wave meter has to be placed in between oscillator and attenuator. So why we place this wave meter? To know the frequency of microwaves produced by crystal oscillator. So wave, in the wave analyzers, in the electronic measurements, we have the word wave analyzers. So you know this frequency of the microwave produced by the crystal oscillator. And wave meter usually calibrated in frequency in the order of megahertz instead of wavelength. Right? The waveguide looks like a hollow rectangular glass tube. It is used to convey the wave radiation to sample and crystal. To the sample and crystal. So the power propagated down the waveguide may be continuously decreased may continuously decrease by inserting a piece of resistant material into the waveguide. So it is a power control. You want to control it. That piece is so called alternator, variable alternator. This variable alternator we can control the power. And and this alternator is used in varying power of sample from full power of crystal to one attenuated by force 100 or more. So we can decrease the maximum power to some level of the power with this uh, power crystal. Power means waveguide. Okay, then uh, then see how this is a microwave setup. Is a microwave setup. Right? Sample port and some electromagnetic field, and some from these reflections we can get some electrical field. Electric field. Okay, this is complete structure of the ESR. So this is a frequency counter. From this we have to know the frequency. Frequency counter uh, or frequency meters. It gives some frequency that is given to micro stabilizer. From this, you can have some micro frequency from the Kickstron, and through some oscillator, some variable attenuator, that frequency is directed to cavity. In this cavity, there is a sample. This sample is placed between some hollow, this some magnetic field, this some magnetic field. From this, that is given to variable attenuator, oscillator, and crystal detector. Crystal detector. So crystal detector detects the reflections coming from this cavity, from this channel, and that detect output detects by this detection. Output detector is going to give some amplifier and some multimeter. So basically, it is a diode detector which converts that emitted radiation into variable current, That current is metered. So how much current is decreased? Nothing but that much of absorption is going on in the sample. That much of microwave frequency is absorbed in the sample. So based upon that, we can easily estimate that sample analysis. Sample analysis. Okay, and this is a simple principle of this uh, uh, ESR, electron spin uh, resonance, electron spin radiation. Basically, if you see that, if you see uh, if you see this, the basic idea regarding this, what happens, what happens, uh, so there will be weaker radio frequency alternating magnetic field having the frequency of process of electrons applied at right angle. Okay, before this, see this, see here, uh, the phenomena of electron spin resonance is based on the fact that an electron possesses a spin, that is known, and associated with the spin there is a magnetic moment. The value of which is called the Bohr magneton. So what happens, the atoms, ions or molecules having an odd number of electrons exhibit characteristic magneton properties, so which arises from spinning or exhibiting action of the unpaired electrons about the nucleus. So there will be about the nucleus, we can see there are some unpaired electrons. Unpaired electrons means what? Single electron. Is it? electron. So that single electrons is have a major role in this ESR, right? Um, See what happens, exhibit as a magnetic the ions. The ions molecules having an odd number of electrons exhibit characteristic magnetic properties, okay, which arises from spinning or exhibiting or orbiting action of unpaired electrons, unpaired electrons about the nucleus, unpaired electrons. So, whereas for these unpaired electrons, if you apply a strong magnetic field, then what happens? The electrons will be split into two groups. For unpaired electrons, if you apply a, a magnetic field, the electron may split into two groups. So what happens in the group? The electron dipoles or magnetic moments of electrons are aligned either parallel or anti-parallel to the direction of the external magnetic field. Okay, the electrons will process about the axis of the magnetic field at a frequency proportional to both the applied magnetic field and electron magnetic field. So, because of the single electron, unpaired electron, it gives some its own magnetic field parallel to the available magnetic field. So, what happens? The weaker radio frequency alternating magnetic field having frequency of uh, precision of the electron is applied at right angle to the fixed magnetic field. Resonance occurs. Resonance occurs. So when resonance occurs, what happens? Spin occurs. So at resonance, the absorption of energy from rotating field causes, yeah, spin of electron to flip from the low energy levels to higher energy levels. So whenever spin occurs, the electrons in the low energy, I mean, uh, the atom, the atom in the low energy state may excite to high energy level. So we can separate the two energy levels by capital E equal to h nu equals 2 mu h, 2 mu h. So in this, uh, H refers to magnetic strength, magnetic field strength. U nothing but permeability, nothing but it, and E nothing but the difference between two energy levels. H is the Planck's constant, V is the frequency. So, uh, so this can be right. This V can be right 2 mu h by mu h. Or if we rearrange like this, you can get the frequency depends upon this. The frequency depends upon the magnetic field strength. Magnetic field strength. So, in a field of 3,400 Gauss, the precise frequency is approximately 9,500 megahertz. What we said, what we, I mean, selecting a frequency from electromagnetic spectrum. This frequency we are selecting. This is called X X band. In actual practice, the radio frequency is in the microwave region and is held at certain constant value. And the magnetic field strength is varied to obtain conditions. Yeah. So by varying the magnetic field strength, what happens? That is varied obtain conditions where resonance occurs. So if, yeah, capital H is going to be varied, V is going to be varied. So the sample depends upon capital H and small v. The sample to be analyzed. Of course, it is a difficult to understand you. It's completely the theory behind this. Complete theory behind this. Okay, quantum theory. Quantum theory. Okay. The incident radiation is absorbed by the electrons in the low energy level and they may jump into high energy state. In general, what happens? In general, If N1, the population of a ground state, exceeds N2 population of exile state, a net absorption of microwave radiation takes place. The signal would be proportional to population difference N1 minus N2. This is what happens. By the Boltzmann distribution law, the population radiation ratio E in the two states given by N1 by N2 equals to E power minus 2 mu h by kT, where k is the Boltzmann constant. The sensitivity of measurement is greatly enhanced by using a high magnetic field. So, if you want any spin for a particular electron, if you want any spin, depends upon h and nu, h and nu, h and v, small u. By changing the h, you can change the frequency, so that spin of the unpaired electron is going to be changed. You may get some reflected radiation. They are going to measure with the microwave detectors, which converts into a DC current. DC current. Based upon the amount of decreased current for a particular uh, graph, particular lines, what we detected from the sample after absorption, we can easily analyze that sample of the structure, sample of the structure, or molecules of the structure, chemical structure compounds. Okay, this is the theory behind this uh, in this um, electron spin resonance. Okay, if you have any doubts, you can feel free to ask. Now, up to this, we are completed the two chapters. This is for your midone examination. Okay.